Lithium-ion batteries. They come in all sorts of shapes and sizes. You get them in your phones, tablets, drones, and electric cars. But what actually are they? Stick around and find out.
Lithium-ion batteries are rechargeable chemical cells in which lithium ions move from the anode through the electrolyte into the cathode, causing a flow of electrons when connected in a circuit. They produce a higher voltage than other mainstream battery technologies such as lead and nickel-based batteries, and they generally have higher energy and power densities. It's important to carefully choose materials to maximise the lifetime and efficiency of the battery.
Sam, that is extremely interesting, but could fools like you and me ever actually make one of these things?
It's funny you should say that. I made some earlier, and here is how it's done.
Start by transferring electrode materials to the glove box. Evacuate and repressurize antechamber 3 times. For this chemistry, measure out 1.92 grams NMC, 0.04 grams PVDF, 0.04 grams C45. Mix. Transfer to container and add 1.17 ml NMP. Maybe better than Liam did it. Let's try that one again. Remove the container from the glove box and put it in the thinking mixer. Set it at 1500 RPM for 5 minutes. Meanwhile, cut 1 sheet of the current collector. When the thinking mixer is finished, remove the container. Place the current collector sheet on a flat vacuum bed. Add electrode slurry. Spread. Heat at 85 degrees for 1 hour to dry. After cutting the sheet to size, reduce the thickness of the electrode between 2 rollers. Punch the electrodes into discs for coin cells and transfer to container. Back in the glove box. Clean a small sheet of lithium using pretty much anything. Here we've used the back of a common household syringe. Punch the lithium into a disc. To assemble a half cell, start with the bottom casing and add 1 spacer. Add the lithium electrode. Add the separator. Add 10 drops of electrolyte. Finally, add the other electrode and put on the top casing. Put cell in crimping machine. Lock it. Load it. Release. Remove constructed cells from glove box.
And this is what you end up with. 1 battery safely sealed in this CR 2016 coin cell housing.
I have to say, Sam, that's very impressive. Well done. But does it actually work?
To be honest, I don't know, but let's go and try and find out.
Start by putting the cells in the testing rig. Follow the wires and ensure it's plugged into the correct channel on the Mac or cell tester. Select your program to run and leave to test.
So, it turns out that they do actually work. We even tested adding some FEC to the electrolyte to help them perform better. Watch this and we'll explain how.
The capacity of a battery is related to the number of lithium ions available, and we generally measure it in amp hours, which is the total current discharged over a time period. However, this capacity is not consistent on the first charge cycle. When the cell is first charged, lithium salts in the electrolyte react with the graphite anode to form a layer known as the solid electrolyte interface. Unfortunately, the lithium ions consumed when this layer is formed are no longer available to act as energy carriers, so the capacity of the battery drops. So we added FEC to our cells in order to reduce the loss of lithium ions. FEC reacts at the graphite anode, forming a polymer layer that coats the surface. This reaction occurs preferentially to the lithium salt reaction, and hence less capacity is lost during the first charge.
Without using FEC, we found our cells to have an average capacity of 92 milliamp hours per gram, and when using FEC, the capacity was 107 milliamps per gram, which is a massive 16% improvement. FEC even helps improve the cycle life. Just look at this graph. As you can see, it also changes depending upon which charge method we use. To better understand the mechanisms, we also looked at the cells through a microscope. As you'll see, there is obvious degradation in the anode material after cycling.
The cathodes show different sized NMC particles. It's also possible to see the binder between the particles. It's noted that there is no change between the fresh and degraded cell. With the anode cells, the graphite particles are clearly seen. The surface is relatively smooth and parts of binder and separator can be seen. With the degraded cell, the surface is clearly more broken, which is likely due to the pore formation of the SEI. And comparing the two, it's reasonably obvious which cell is degraded.
I hope this has helped you understand something about lithium-ion batteries. This video has been produced by the Sheffield Energy Storage CDT. You can click here to find out more about our group, or you can click here to see our full report on lithium-ion batteries.